What's going on, guys? Today we'll be covering the second half of chapter 1. We will cover mean squared error, error rate, the Bayes error rate, variance, covariance, and correlation, and then we will look at some plots. So today's going to be mainly math focused. Mean squared error. So mean squared error is a commonly used metric to measure the performance of a regression problem. So we learned last video that a regression problem is when we have a dependent variable that is numeric. So in this case we're predicting shoe size. So we're going to use gender and height to try to predict shoe size. So the formula for mean squared error is going to be the summation of the observed value minus the predicted value squared divided by the degrees of freedom, which in this case we're just going to use n. But this number will change once we start introducing different models. So this observed value minus predicted value is also known as a residual. So this can be read as the sum of squared residuals divided by the degrees of freedom. So solving for it, we're going to get, we observed a value of 12 for shoe size, and we predicted a value of 11. So it's going to be 12 minus 11 squared, plus we observed a value of 11 but predicted 12 squared, plus 7 minus 9 squared, plus 8 minus 6 squared. And then divided by the degrees of freedom, which we said we're just going to use n, which is just the number of observations. So it's going to be 1, 2, 3, 4. And then solving for this, we get a value of 2.5. So our goal is to minimize the mean squared error. So a smaller value means a better model. So now we have the error rate. So the error rate is used for classification problems, which means we have a categorical dependent variable, which in this case we're predicting whether or not it's going to rain. So it's a yes or no. So the formula for that is just going to be 1 over n times the summation of the identity of the observed value does not equal the predicted value. So what that means is if they're equal, we're just going to return a value of 0. If they're not equal, we're going to return a value of 1 and then divide it by the number of observations. So for instance, the actual value was it did rain that day and we predicted it would rain that day. So it's going to be a value of 0. Now on this day, it didn't rain, but we predicted it did. So we're going to give that one a value of 1. And then on this day, it didn't rain, we predicted it wouldn't rain, so give it a value of 0. And this day, it did rain, and we predicted it would rain, so we give it a value of 1. We divide by the number of observations, which is 4, and we get a value of 0.25. So the error rate is 0.25, or 25% of the time we predicted wrong, which would be this observation here. Bayes error rate. So Bayes error rate is also used for classification problems, or we have a categorical output. And what this formula is saying is that if we're given the probabilities of different possibilities happening, we always guess the maximum probability. So for instance, if you go to the arcade and you ever play that game where you drop a ball on the spinner and you want to guess what color it's going to land on. So let's say about half of it's blue, maybe like a sixth is red and the rest is green. So if we wanted to guess the color that's going to land on, most accurately we would guess blue every time. So we'd be right 50% of the time. So what the Bayes error rate is the time we will get wrong. So it'll be 1 minus the times we get right, so we'd get 50% of the time we would guess wrong. Now that can be extended to more than one predictor. So in that case it would be like one predictor. Here we're going to have 2 predictors. So let's say we're trying to guess whether a person is a male or female. So we're going to give the probabilities in male, and if it's not a male, then of course it's a female. So if we create a table of whether they have long hair or short hair, and whether they're tall, medium, or short for their height. So the given probabilities, and these would have to be given to you on the exam, and generally in practice these aren't known. But let's say if we know that every long-haired person that is tall has a 50% chance to be a male, and a long-haired person that's medium height has a 40% chance to be a male. Long hair is short, we'll say 0.2. Now if they're short hair and they're tall, we'll say 80% chance to be a male. Short hair and medium height, we'll say 70%. And then short hair and short, we'll say 40%. Okay, so for a long-haired, tall person, they have a 50% chance to be a male. So what that would look like on our spinners, 50% would be red, or male. So no matter whether we guess male or female, we'll be right 50% of the time. So we can just guess male. Now for the next observation, we see a long-haired, medium height. There's only a 40% chance to be a male. So in this instance, we would guess female, and we'd be right 60% of the time. Now if they're long hair and they're short, there's only a 20% chance to be a male. So we would guess female, and we would be right 80% of the time. So now if we do the same for the other side, 80% chance to be a male, so we're going to guess male. 70% chance to be a male, so we'll guess male. And this one only a 40% chance to be a male, so we're going to guess female. And then if we just divide this by the number of boxes, which here is 6, we're going to get a value of 0.67. So this will be the amount of times that we guess correctly, 67% of the time. But we want to find the error rate, or how much we guess incorrectly. So that's just going to be 1 minus 0.67, and we're going to get a value of 0.33, which is our Bayes error rate. We can solve for variance, covariance, and correlation. So the variance measures the spread of a variable. So the sample variance of x is equal to s squared subscript x, which is equal to the summation of x minus x bar squared divided by n minus 1. So the first step will be to solve for the mean of x, which is x bar, which is going to be equal to 12 over 3, which is equal to 4. So now plug it in, x minus x bar, so 4 minus 4 squared plus 3 minus 4 squared plus 5 minus 4 squared divided by n minus 1, and n is just the number of observations, so 3 minus 1, and we get a value of 1. Now the sample variance of y follows the same formula, so we find the mean first, which is going to be 15 divided by 3, and we get a value of 5. So just plug it in. We're going to do 6 minus 5 squared plus 4 minus 5 squared plus 5 minus 5 squared divided by n minus 1, which is going to be 3 minus 1. And we're also going to get a value of 1. Now the covariance of xy. So the sample covariance of xy is going to be equal to the summation of x minus x bar times y minus y bar over n minus 1. So we already found the mean of x to be equal to 4 and the mean of y to be equal to 5. So then it's just plug it in again. So x minus x bar is going to be 4 minus 4 times y minus y bar, just 6 minus 5, plus 3 minus 4 times 4 minus 5 plus 5 minus 4 times 5 minus 5 divided by n minus 1, which is just 3 minus 1, and we're going to get a value of 0.5. And now finally, correlation. So correlation is just equal to the covariance of xy over the sample standard deviation of x over the sample standard deviation of y. So we already solved for these terms. So we found the covariance to equal to 0.5, and we found both the sample variances to equal 1. So sample standard deviation is just equal to the square root of the sample variance. So it's going to be the square root of 1, square root of 1, and we're going to get a correlation of 0.5. So correlation measures the relationship between two variables. So positive correlation means as one increases, we expect the other to increase. And negative correlation means as one increases, we expect the other to decrease. So now we're going to do another correlation example. So we just found that the correlation is equal to the covariance of xy divided by the standard deviation of x times the standard deviation of y. So if we cross out the n-1 terms, what we're left with is the summation of x minus x bar times y minus y bar over the summation of x minus x bar times the summation of y minus y bar. Now these terms can be broken down further, so the summation of x minus x bar times y minus y bar is equal to the summation of xi yi minus the summation of x summation of y over n. And the summation of x minus x bar is equal to the summation of xi, or the x terms squared, minus the summation of x times the summation of x over n. And then that can be the same way applied to variable y. So if we're given, instead of the covariance and standard deviations, instead we're given terms like this, the xi squared, xi, so on, we're still able to solve for the correlation. So we found that the correlation of xy is equal to the covariance of xy over standard deviation of x times the standard deviation of y. So now instead of using these terms, we're going to plug in these terms in their place. So we can do the covariance of xy is equal to the summation of xi yi minus the summation of x times the summation of y over n. And then for our denominator, we can do the square root of the summation of xi squared minus the summation of x times the summation of x over n times the square root of the summation of yi squared minus the summation of y times the summation of y over n. And then it's just plug it in terms. So for instance, summation of xi yi, which we can see here is 150. We'll keep it blue. It's going to be 150 minus summation of x, which we see here is 10, times the summation of y, which is 100. And then divided by n, which is 10. And then for the denominator, it's going to be summation of xi squared, which we can see is 260, minus summation of x, which is 10, times the summation of x, which is 10, divided by n, which is 10. Take the square root of that, and we multiply by summation of yi squared, which is 1040, minus summation of y, which is 100, minus summation of y, which is 100, over n, which is 10. Take the square root of that. And plug it in. You should get a value of 50 over 100, which is equal to 0.5, or a correlation of 0.5. So memorizing these is actually pretty important because it won't just be used for correlation. We'll also be using these once we start getting into estimating our parameters for linear regression models. So as you can see, these are pretty much the same. It's just one x, one is y. And then for here, it's just instead of x squared or y squared, since there's x and y, it's just going to be xi, yi, xi, yi, instead of these two repeating. So if we're given values like in our first correlation example, where we're given the x values and the y values, we're able to find the correlation on our calculator. So if you go to stat, and then you fill in the values for x for the list 1, you fill in the values for y in the list 2, you hit second stat, 2 variable statistics, and then enter, and then you scroll down to where it says r equals, that'll give you the value of correlation. So if you want to plug, these are the same numbers from the first example. If you plug it in, you should get a value of 0.5, which we found earlier. Plots. So the first types of plots we're going to talk about are univariate plots. So univariate plots just means one variable, or it only shows one variable at a time. So two examples are going to be density plots, also known as PDF plots, or probability density function. And what they do is they represent the density of a variable. So for instance, it might look like this. On the scale, we might see about 30% at its peak. Now histograms represent similarly to a density plot, but instead it bins the variable and it gives counts. So for instance, for the same variable, it might look something like this. So it's just grouping the observations, say every 20 observations, and then it's counted how many fall within that interval. So essentially, it's a density plot is just a smoothed version of a histogram, but then the y-axis is going to change scale-wise. Histogram. QQ plots, also known as quantile-quantile plots, are used to test whether a variable comes from a certain distribution. So if it does follow that distribution, it should form a straight line. Now if it doesn't form a straight line, we can say that variable does not follow that distribution. So it's usually used to test whether a variable is normally distributed or not. In which case, on the x-axis, we will have z-scores. And then on the y-axis, we will have the sample quantiles. So on the x-axis, we have z-scores for normal distribution. These are also known as the theoretical quantiles. So if it follows the distribution that you're proposing it does, so the theoretical is equal to the sample quantile, you will get a straight line. If not, then it will not follow a straight line. So for here, we can see that this variable is not normally distributed. So far we looked at univariate plots. Now we can look at a bivariate plot, or it depicts two variables at once. So what we have here is called a scatter plot. So scatter plot shows individual observations mapped between two variables. So here we have variable x1 and variable x2. And from this we can see that as variable x1 rises, variable x2 rises up to a certain point, and then as x1 rises, x2 starts to decrease. So with this information, it'll help us model our problem. And here we can see that x1 and x3 have a positive linear relationship, or as one increases, we can see that the other also increases. Box plots. So box plots also measure only one variable at a time, and they're also known for giving the 5-number summary. So this 5-number summary gives two whiskers, which represent the edge of the outlier range. The 25th percentile, or 25% of the values are less than this value, the median, and the 75th percentile. So the rectangle length or the 75th percentile minus the 25th percentile, is also known as the IQR, or interquartile range. And the whiskers can be solved as the 75th percentile plus 1.5 times this IQR, and the lower whisker can be solved as the 25th percentile minus 1.5 times this IQR. And anything past these 1.5 times the IQR plus the 75th or minus the 25th are known as outliers. So here we see in green, this is the IQR, blue is the whiskers, and red is the outliers. So if we were to solve for our own box plot and we're trying to solve for the whiskers and we're given the 25th percentile, the median, and the 75th percentile, our first objective would be to find the IQR. So the IQR is just the 75th percentile minus the 5 percentile, which is going to be 11 minus 5, and we get a value of 6. Now the upper tail is going to be this tail here. It's just going to be equal to the 75th percentile, which is 11, plus 1.5 times the IQR, which we found to be 6, and we get a value of 20. Now the lower tail, which is just the 25th percentile, just 5, minus 1.5 times the IQR, which we found to be 6, and we're going to get a value of negative 4. So this tail, since there's a negative 4 in the variable, is going to span all the way until negative 4. But if you've ever looked at box plots before, you notice that these tails a lot of times aren't the same length. So that's because they snap to the last observation that is smaller than the end of the tail. So for instance, here's our variable that this box plot's depicting. So we have, if these are in order, we have observation with a value of 16, 17, and then jumps to 23. But our value is 20. So this tail's only going to stretch to value 17. Now if we had a value of 20, or a value of 20 is added, this will instead stretch to 20. But since we don't, it'll stop at 17. Now our outlier range is still anything above 20, so we have one observation, which is 23, which would be an outlier. At this point, we're just going to do some proofs. If you're not really interested, you can just skip the rest of the video. At this point, you should be able to answer all the practice problems. If you haven't read the chapter notes yet, I suggest you skim through those. And what we're going to be solving for is why use n-1 in the sample variance, why is there no unbiased correlation, and then why those summation formulas that we worked out for correlation before make sense. Okay, so why n-1? So if we're just solving for a population variance, we do the summation of x minus x bar squared over n. But when we use sample variance, we do the summation of x minus x bar squared over n minus 1. So the reason for this is, say this is our sample here, and we have 5 observations. Now if we know that the true population mean lies right here, but from our sample we would get a mean right about here. So the problem with this is that the sample mean is actually influenced by the observations in it. So although these observations are much higher than the population mean, which means they should have a high variance, the sample mean will be pulled towards these observations, which will make the variance look much smaller. So by dividing by n-1 or a smaller number, you make the variance bigger, which is how you address for the bias of this. So we divide by n-1 to make the variance bigger so that it can adjust for the sample variance being pulled by the sample mean instead of the population mean. Okay, so hopefully that makes sense. Why is there no unbiased correlation? So we found earlier that the correlation is equal to the unbiased covariance of x and y over the unbiased standard deviation of x times the unbiased standard deviation of y, which breaks down into this formula. So as we can see here, we're going to have on the numerator we're going to have divided by n minus 1, and the denominator we're going to have divided by the square root of n minus 1 times the square root of n minus 1. So these n minus 1 terms ultimately end up canceling. So what you're left with is just summation of x minus x bar times y minus y bar over the summation of x minus x bar times y minus y bar. So no matter what value we use for n, the correlation won't change, which is why there's no unbiased correlation. And then this is our final proof, and this was used for the correlation terms we used in our second example. And essentially I'm just going to be ending the video now, but ultimately if you do want to dive through this, you'll find that these terms do equal out, no matter if you use a summation from 1 to here, it's just an example, to 3 to shorten it, but no matter what n you use or number of observations, it'll ultimately break down to this. And so that's all I got. I hope you enjoyed. Good luck on the practice problems. If you have any problems with them, please leave your questions in the comments and I'll try to answer them. Thanks.